Let's talk about the radius of convergence of the power series solution to this specific differential equation. Now, first of all, you need to have the concept of the standard form. You change this into a standard form by dividing by the coefficient of y double prime. So you divide this so that the equation looks like y double prime plus some other things, okay? So as long as you isolate this y double prime like this one, that's called the standard form. Then we can talk about the singular value of, or singular values of this differential equation, which is any value of x, including complex numbers, that makes the denominator equal to 0. So, so sometimes you might have like this one will be 1 over x minus 3, and this one will be 1 over x minus 2. Then both 3 and 2 will become singular values of this differential equation, okay? All right, so you can kind of see that when you have the denominator equal to 0, then this differential equation will be ill-defined and something will happen there, right? That's exactly the point. That's why we have such a thing called singular values. All right, so we set the denominator x squared plus 5. Since they are the same, we just have to solve this one equation. If they are different, we have to solve both of them, and any solutions will be singular values. So there can be many singular values for a given differential equations. Okay, so we take this and move the 5 to the other side and take the square root. Well, when you take the square root, you better have plus or minus, and then the square root of negative 5 can be broken as square root of 5 times square root of negative 1. And this is what we call the imaginary number. We write it as I, and if you're an engineer, you would write it as J. So that's it. These are the singular values of this differential equation. All right, so what? Well, when it comes to differential equation and power series solutions, the singular values are the ones that give you the radius of convergence. But maybe you don't remember what radius of convergence is, so let me just give you some idea. Well, if you have a power series like this, then it's not true that this will always give you a value. If you have a value of x that's too big or too small, sometimes it will give you a nonsense value. So as an easy example, if you have like say a0, a1, a2, these are all ones. Of course, that's not going to solve this differential equation, but let's just say that you have such a power series. So a very simple one, just 1x, x squared. Now, you can easily see that if x is 1, then there's no way this can converge, right? If x is 1 and you're just adding ones over and over again, so it's not going to converge. Same goes for 2 and 3. Also, same goes for, say, negative 2 or negative 4 or something like that. But if you have something less than 1, this does converge. So if you have, say, x is 1/2, then 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. That actually converges to, let's see, I think it's going to converge to 2. Yeah. So it does give you some finite value. So you can kind of see that for a given power series, sometimes there is a limit to what x can be, and so you end up with this interval of convergence, and the radius of that interval, or half of the width of the interval, is called the radius of convergence. Okay, so now that you know what radius of convergence is, hopefully you remember, we can go back to this discussion here. The radius of convergence of a power series is a legitimate question to ask, but there is a very simple criteria, which is that the radius of power series is the distance from the origin to the nearest singular point. Okay, so what does that mean? Well, this only makes sense in the complex plane. So, hopefully you remember what complex plane is. Like, here's the real values here. That's the real number line, but here's this imaginary axis here, and that gives you a complex plane. And over here, there's the positive square root of 5i, and there's another one, negative square root of 5i. And actually they're equal distance to 0, so you can't say which one's closer. In that case, just choose one of them. So let's say this one. And then the radius of convergence of any solution of this differential equation, except for the case that it just is finite. It may just sometimes get a finite terminating solution sometimes. Maybe not. Okay, I guess. Okay, so any solution of this differential equation will always have the radius of convergence of this distance, see, origin to this nearest singular point. Okay, so that's what we know. So by the way, this absolute value is the distance from 0 to this number on the complex plane. So since I has distance 1, this distance would be square root of 5 to 0. I mean, this picture says it all, right? This distance is square root of 5. And that's the radius of convergence. And what that means is that any power series solution to this will converge if x is between square root of 5 and negative square root of 5, right? Because that's the radius. Now, what I'm not showing you here is for the case when you have a power series solution centered at numbers other than 0. So you can look at my YouTube channel and look for power series solution around x equal to 1. That's also another possibility. That one will be different because now you have, for that case, you have to now think about the distance between square root of 5i to 1, and that distance will be the radius of convergence for that case. So that's another case. But at least for the case when you have a power series solution expanded around 0, which is what we are doing, this will be the answer. So this is the interval of convergence, and this will be the radius of convergence.